Okay. Okay, we can start anytime. We can start. All right, good afternoon. I'll start by reviewing what we talked about last time. We discussed the topic of charge sheet model. Its purpose is to find an approximate expression for Q inversion as function of Vg. I will not review any of the equations that we presented last time. Even the approximate expressions are still fairly long, and it's unlikely that you will use that for hand calculation, with one exception, that is in the subthreshold or weak inversion region. And weak inversion region is kind of defined between the region of phi s equal to larger than phi b and less than 2 phi b. All right? That's also the condition when the surface electron concentration is larger than the surface hole concentration. Larger than the surface hole concentration, but smaller than the doping concentration. All right? So that would be the case that we limit ourselves to. If we limit ourselves to this weak inversion region, then we arrive at several simple relationships, and it's important to remember this. That is the inversion charge density. It has the units of Coulomb per centimeter squared, not centimeter cubed, but centimeter squared, is proportional to exponential beta phi s, right? And in fact, we did derive even the pre-exponential factor here. Secondly, we say it's proportional to exponential QVG over KTN. And this just simply means that phi s and Vg are linearly related. Particularly this n is always larger than 1, meaning we need to apply more than, say, 60 millivolt of Vg in order to create a 60 millivolt change in the phi s. We may have to apply a 90 millivolt change in Vg in order to create 60 millivolt change in phi s, and that's reflected by this n. So n is always larger than 1. And specifically, n is equal to 1 plus depletion capacitance over oxide capacitance. And you can understand that by this equivalent circuit. We change Vg by a delta Vg. As a result, the surface potential is changed by delta phi s. This is the oxide capacitance, this is depletion capacitance. Okay, so that's the charge sheet model. Any questions about charge sheet model? All right, now we're going to a new section, 3.5. And 3.5 is, well, this is not new. This is also a review, but we will continue with this section today. We did mention at the end of last lecture that sometimes there is charge in the oxide. There are several kinds of charge in the oxide. I'll start by talking about a simpler kind. That is what we talked about last time. It's called oxide fixed charge. Oxide fixed charge almost happens always right at interface. At least that's the assumption, right at the interface. All right? When we model this mathematically, we always assume it's right at the interface. When we discuss the physics, certainly interesting to ask the question, is it really right at interface? What is the interface of a SiO2 and silicon system? We can gradually refine those concepts. But for all practical matters, these charges believed to be right at interface. In fact, literature usually claim that these are essentially silicon ions. All right? So they're always positive. So at the SiO2 and silicon interface, we always find some positive charge. And this charge do not change regardless of our bias conditions. So we know they're fixed. In that sense, they're fixed, all right? Unlike interface traps, they don't get changed. And they're always positive. We call these oxide fixed charge, all right? Now, we could try to change this QF using process changes. In other words, when we oxidize the oxide, how do we oxidize it, and how do we anneal it afterwards? The goal has always been to minimize this fixed oxide charge. It's considered undesirable. It does have some impact on mobility. We'll mention that later, perhaps. But fixed oxide charge is considered undesirable, so we try to minimize that, and so it's usually less than this. This is what we can create. Unless we're talking about a new dielectric process, a new dielectric material, then everything is possible, right? So people will pay a lot of attention to what that interface is. But if you're talking about a production-worthy SiO2 dielectric process, you can expect to be only about 10 to the 10s. Now, may not be less than, but we can make them less than, let's say 10 to 10s, around that, all right, of that order. Next, I want to estimate with you what's the impact of this charge. I guess I did mention already that it could have an impact on mobility, but mobility is not the topic of Chapter 3, so we're not going to say much about it, all right? In this chapter, we'll just stress the effect on threshold, on flat band voltage, remember? Any charge in the system will change the flat band. And why are we concerned about flat band? Well, we don't worry too much about flat band voltage, to be frank with you. We are more worried about threshold voltage, right? To the extent threshold voltage is related to flat band voltage, of course, we're concerned about flat band voltage. But it's really not flat band voltage per se, it's the threshold voltage. We want that to be very stable. We want to make sure that every lot coming out has the same threshold voltage, right? So we don't want to say this QF is changing or all right. So what's the VT is equal to phi ms plus 2 phi b, QB over Cox, I guess, to be really exact about this. And I'll use a red pen where I want to ask Kevin to change this slide for me. I guess I really should say minus, all right? I apologize for this confusing. I have not been consistent with the notation. And so in general, should always be negative, all right? Always should be minus. Should be minus, okay? And this delta Q is whatever charge we put at interface. If we're talking about a specific example of fixed oxide charge that we call QF, then I should replace this with QF. All right? Okay, I just want to say, sort of I guess I'm planting the seed that there may be other charges in the oxide. But certainly the fixed oxide charge is 1. So if it's fixed oxide charge, we'll call this minus QF over Cox. And that's all we want to know, really, is this is the VT. Whether you redefine the flat band voltage or not is really not material. But in reality, we do redefine VFB. We would lump this together with that term, put them together and say the sum of these is the new flat band voltage, all right? So flat band voltage does change, and certainly threshold voltage should change very simply from our relation, relationship of VG in general is equal to phi ms plus 2 phi b minus any charge in the substrate divided by Cox. So if you consider part of the charge in the substrate, that's fine. If you want to add this to VFB, then of course this term no longer is considered as part of substrate charge, becomes part of VFB, right? So either way, how you want to think about it, the results is the same. All right. So what I want to do is to go through the magnitude with you. Suppose we say QF is 10 to the 10th per square centimeter. What impact on VT are we talking about? In order to evaluate that, we have to know what Cox is. Is that right? So what is Cox? Well, this is what I kind of remember this. You don't have to memorize it this way, but that is for 100 angstrom of oxide, you get 3 femtofarad, okay, 10 to the minus 15 is femtofarad. Okay, 3 femtofarad for 100 angstrom of thickness. And I can tell you a few years, used to be, people memorize this way, that is 1 femtofarad per micron square, by the way, I should have said micron square, as oxide capacitance for 321 angstrom of thickness of oxide happens to be the number, so it's a number that's the reverse of 123, so a lot of people remembered that. But roughly speaking, 100 angstrom give you 3 femtofarad, all right? Now, with today's number, perhaps we're back to thinking 32 angstrom will give you 0.1 femtofarad. I'm sorry, 10 femtofarad. That will be just fine, right? Because the thickness we're dealing with is more like that now. So you can think 30 angstrom will give you 10 femtofarad. That's one way to remember it. All right? Okay. Here I use the example of 100 angstrom that will give 3 femtofarad. So the effect of this charge on the delta VT will be equal to, the charge is 1.6 times 10 to the minus 19 times 10 to the 10th, 10 to the 10th. Is that right? Okay. Divided by C, ox, is 3 femtofarad in this case. Is that right? Yeah? But that's per micron square. In the numerator, we're talking about a charge per centimeter square, right? So this is the femtofarad per micron square, and in each centimeter square, there are 10 to the 8th micron square. Yes? You all know that, right? Okay. So then you end up with 5 millivolt. So what type number we're thinking about? We're talking about, so today if we're talking about what's expected quality of SiO2, the impact on the VT is very small. It's really very small. So we really are concerned about this only if we're talking about a new process, a new technology, deposited oxide or high K dielectric, then of course we are concerned about this fixed charge. Otherwise it's not very large. Number one, okay? Number two, will this number increase or decrease as we continue to reduce the dielectric thickness? What would do? Decrease, right? Because Cox will be increasing. Is that right? So we expect this to decrease. So the effect of this charge on VT is getting less important, in case you have some experience with this type of problem. Years ago, we were more concerned about it. Now we're less concerned about it. All right? On the other hand, the impact of this charge on the mobility through scattering, Coulombic scattering, do you think that's going to become less important as dielectric thickness becomes thinner? You think it's more important. Why do you think will be more important? Speak into the microphone, please.
I think it might be due to the electric field. Maybe get more intensive than the large dielectric thickness.
All right. Well, there may be some reason that is going to be more important, but at least there's no reason to think it's going to be less important, right? Suppose we have some interface charge right here, and they scatter electrons and reduce the electrons' mobility. Now, whether the oxide is 100 angstrom thick or 20 angstrom thick, as long as QF is not getting smaller when we make this oxide thinner, which is unlikely, then its impact on mobility will always be there. Is that right? So, yes, so perhaps this oxide charge will become less important in terms of impact on flatband voltage and threshold voltage, but we expect them to continue to be important in its impact on the mobility, and perhaps will maybe become more important, something we're going to watch. Yes?
Wouldn't more of the charge, as the aspect ratio of the device actually scales, the amount, more of the charge occupies, it's closer to the actual interface, right?
Are you talking about the Q inversion charge now, or this fixed oxide charge?
Inversion charge.
Inversion charge, all right. So you expect as things scale, it will get closer.
Right.
All right. Now, last time in the discussion session, we talked a little bit about what determines the closeness of the interface of the inversion electrons to the interface, and we introduce a term called centroid. Equivalent name is inversion layer thickness. What determines the centroid of inversion charge and the thickness inversion layer? It's solution of Poisson equation, right? But what determines the thickness of that Poisson equation solution of the wave function? Well, has got to be the electric field at the surface. Is that right? Has got to be, or it has a lot to do with it at least. All right? Because that gives you the potential well, what kind of shape it is, right? And this field is also related to the field in oxide through a factor of 3 ratio, right? So basically the question is, do we expect we're going to use much higher field in the oxide as we continue to scale the device? Well, the answer turns out is that we're not going to be able to apply much higher field. We're pretty much going to stay at the field we are. We may creep up a little bit. We're not going to be talking about much change now because we're so close to breakdown. All right? So as you know, the last few generations, the trend is that oxide has been scaling roughly in proportion, power supply's voltage has been scaling roughly in proportion to the oxide thickness. All right? So we actually are not going to expect significant change of the separation between the charge and interface. But indeed, we do expect some incremental increase, and that's one reason I agree with the statement earlier. They will be closer, so there may be even more interactions, maybe more scattering. But we're not going to be able to increase the vertical field that much. That's one of the difficulty of scaling we will see. Okay. We're already using, 20 angstrom of oxide. How much thinner can we make it? Right? Okay, other comments. Good comment. All right. So that's the magnitude to keep in mind. All right. All right. There are other traps I want to mention. There's the oxide bulk trap or bulk charge. In other words, the charge does not have to be simply right at the interface. There could be, charge in the bulk as well. All right? And perhaps these are broken bonds, and they serve, they behave as electron traps. So if the electrons fall into the trap, then become trapped electrons. So those are the names. There's oxide trap, and there can be trapped electrons or trapped charge. Right? Because this is the bulk, so the units tends to be, coulomb per centimeter cube. Right? All right? If we integrate it through the thickness, we can also talk about coulomb per centimeter square. But there's no simple relation between delta VT or delta V flat band with respect to Q oxide. Because what determines delta VT and the delta VFB is the integral of this charge density times x dx. You may recall at the end of last lecture we mentioned this integral, all right? But that's a little bit detail. I don't think we really ever will try to calculate this because we hardly ever know what rho as function for x is, right? How do you know where rho is in a 30 angstrom oxide? If we know the total charge, we're already pretty happy. How can we know where it exactly is? But conceptually, you should know that those charge close to interface have a lot of impact on the VT and VFB. Charge right next to the gate interface has no impact, put this way. In between, it has half the impact on delta VFB, on VFB and VT. Right? It's the charge right next to the substrate interface has a lot of impact on flat band voltage. Charge on the at the gate dielectric interface has no impact on flat band voltage. If you are questioning why, let me draw an image band diagram for you. This is the image band diagram with no charge wherever, right? And if we add some charge at the substrate and oxide interface, this is what we'll have. Band in the substrate is still flat, but because of the interface charge here, the band in the dielectric no longer can be flat. In fact, let me make them positive charge because I happen to know if the positive charge comes down, also positive charge kind of corresponds to our example of the oxide fixed charge. Let's assume it's positive. It will come down, and As a result, the flat band voltage is different. Is that right? Therefore, you created a flat band voltage if there's charge at the substrate interface. Now I'm going to ask you to draw one, using pen on your own notes or just in your mind. How would this energy band diagram change if the positive charge was at the gate interface rather than the substrate interface? All right, I will still define flat band as the substrate band must be flat. So this part is not changing. All right. Now I'm adding some charge to the gate interface. How would this energy band diagram change? How would you change it? To make things simple, let me call this metal. All right, shall we? It's metal, very, very heavily doped poly or metal doesn't make a difference. All right, so don't be too concerned about this gate. Just call this metal gate. How would it change? Now, if you're having a hard time figuring out how this band will change, you got the right answer. There's no reason for anything to change. Right? If this was metal, you have some charge at the surface metal, so what? Right? So that is why charge at the gate interface has no impact. Charge at the substrate has full impact. In between, it's in between. That's where this integral is about. You see what I'm saying? Okay, just try to let you see from this one specific example. It makes sense to try to integrate this. All right? If you are mathematically oriented, just go ahead, solve the Poisson equation for this whole curve. You will find out the voltage created by the charge density is indeed this. That's a voltage created by any arbitrary distribution of rho. All right? Okay. Okay, let me go back to give you another example of a bulk charge or wherever they can be. It's called a mobile charge, oxide mobile charge. And earlier on, there was a lot of debate what's responsible for these mobile charge. Today, there's no question these are sodium ions, and sometimes people believe potassium ions also are present. Sodium ions are present everywhere. If you use glassware in the fab, then your whole fab will be contaminated by sodium because glass is glass contains sodium. And for that reason, we never use, quote, glassware. We use quartzware in the IC fab. They are made of fused quartz, and they are free from the sodium as one way of avoiding sodium contamination. And all the chemicals and the gas also would have to be particularly pure from sodium. If sodium gets into the oxide, sodium has fairly high mobility, such that even at 150 degree or 250 degree, they can move around. And because they are ions, they just move whichever direction the electric field in the oxide wants to move. So what this does is that it creates instability, and that's particularly bad. If the fixed oxide charge give you 50 millivolt very change in the VT, at least you know what it is. You can do a final test of circuit. If circuit works with the presence of this fixed oxide, you can feel fairly confident it's going to continue to work in the next 5 years. But if sodium in the oxide, you never know. After a few months, after a few years in the field where the sodium will move around. As sodium move around between, say, the substrate and the gate, the VT will change. You know what I mean? If VT changes, some sensitive circuit will change, you see? So that's even more problematic, all right? So that's another reason in the fab often test is designed to capture using simple capacitor test structure. We already talked about using simple capacitor, test capacitor to watch for change in metal contamination in the substrate, watch for the change of the generation recombination lifetime, right? But the same test sample can be used to watch for the sodium, presence of sodium. The way you do that is you actually deliberately heat this capacitor on a hot plate and apply voltage to it to see if threshold voltage or flat band voltage or the CV curve moves back and forth as a result of applying voltage across this capacitor. All right? If you see that happen, if the CV is not stable under temperature bias, then you know there is a mobile charge in the MOS system. It's okay? All right. But again, we normally would assume that we don't have this problem, so in this course, we're not going to mention this again, all right? In a manufacturing environment, you should always be aware of this potential problem, but in this course, we're not going to mention this again. Now this leads us to the last item, and the most interesting item, and we're going to spend the rest of the lecture on this idea, is the oxide interface charge. Another term is oxide interface traps. When traps are neutral, we don't have interface charge. When interface traps are charged, then we have interface charge. All right? So that's the relationship. Interface trap, interface charge. Is okay? All right. If we're talking about trap, we usually use the unit of number per centimeter square. All right? We talk about charge, then we talk about coulomb per centimeter square. Is okay? All right. What's the relationship between NIT and QIT? If you say QIT is equal to Q times NIT, then that's not quite right. You haven't captured a subtle difference. That is, not all the NIT will always be charged. They can be neutral. They may be charged. And that's what makes the interface charge different from all these other charge. And that is, interface traps are truly traps. Think about them, traps are interface states. In fact, a older name for this is surface states. If you read older paper, they do use surface states, but in the 80s, I believe, early 80s, IEEE, their standard committee, decided that we should call these interface traps. So surface state is no longer a preferred name for electrical engineers, well, at least the members of IEEE, I would say. But you still see that used. They mean the same thing, all right? So interface traps, think of them as interface traps or interface states. That is, in the band gap, indeed, there's not supposed to be states. But that statement is only true in the bulk of the silicon crystal. At interface, no reason that there cannot be interface states. The amazing thing is that with SiO2 and the silicon interface, there are so few interface states. If you put other dielectric next to the silicon, you actually get a large number of states in the band gap. But with good SiO2 silicon interface, the interface state traps truly has fairly low density, but often can be a problem. Now, what's kind of the density here? Let me give you several numbers. The upper limit probably is number of bonds, number of silicon per centimeter square. If every silicon atom give us interface traps, then we'll be talking about, say, 3 to 5, 10 to the 14ths. Let's say 4 times 10 to the 14ths. All right? That will be the upper limit. It's quite amazing that good oxide can have traps as low as maybe, again, a few times 10 to the 10th per centimeter square. That's very good. But even good oxide, if you now apply some voltage to it, this number will increase. In other words, new traps can be generated just by application of field. So that again becomes a source of instability, just a little bit like that mobile ion. It's instability, it's a reliability concern. Many things can cause the interface states to be generated because we think bonds are broken, including something you might have heard of, that is a hot carrier effect. We'll talk about that much later in the class. I mentioned here just so that you sort of can see there are different things that can cause the bond to be broken and interface trap to be generated. It's for this reason this is particularly troublesome, because even if a material appears to be good, you can do whatever you want to test it, looks very good, but later on this device doesn't look good, the circuit doesn't work, and that potentially is a problem. So interface trap is something we particularly want to pay attention to, all right? And not only that, it also varies in real time. That's the interface trap density can be generated by stress. Interface charge is even more interesting. That is, it actually varies in real time in the order of a nanosecond or microsecond in response to changing of gate bias. The reason is that traps should be really thought of as energy states. Depending on whether those energy states are below the Fermi level or above the Fermi level, then these traps can be filled with electrons or not be filled with electrons. You know what I'm talking about? Therefore, the interface charge will simply vary with Vg. Okay? That certainly have a lot of impact, including, when we're applying Vg, we thought that voltage will give us a change of Q inversion, therefore changing current. It may not, because some of that may be taken up by this NIT, QIT, right? Possible, okay? So including that. That's not one of the most severe concern. Turns out the biggest concern is this QIT also can reduce our mobility, all right? But there are several subtle things about this interface trap that put it in a separate class of the traps or charge in the MOS system. This, I guess, is supposed to mean the interface traps, and I'm sorry, the bulk traps. And again, as oxide gets thinner and thinner, it becomes really almost impossible to separate what is oxide trap, what is interface trap. In fact, I believe it is valid concept that interface traps are really just traps that happen to be closer at interface. If these traps are farther away from interface, that's what we call a bulk trap. That's really what it is, all right? Okay. Any questions about traps so far? All right, so now we're going to concentrate on interface traps and give some more information about that. First of all, there are two types of interface traps. These are called the donor types and acceptor type. What is donor type? Donor type is that they tend to be, they are either neutral or positive. It's just like a donor. If you think about donor, it can be neutral. If it's if it holds its original electron, the fifth electron stays with the phosphorus atom, then it's neutral, right? Think of a donor as phosphorus atom. If it gives up that electron, becomes positive, right? But this phosphorus atom will never become negative. Okay. By the way, there are certain impurity in the silicon that can either be positive, neutral, or negative, but it's unlikely, very rare. So let's not worry about that. All right. So we typically see donor type or acceptor type of traps. Acceptor type, similarly, a boron. If it holds that original electrons, if it doesn't gain an extra electron, it's neutral. If it gains an extra electron, becomes negative, all right? So you see this idea, all right? When we introduce a state, it can either be donor type or acceptor type. Similarly, traps can either be donor type or acceptor type, all right? Okay, and turns out it's very difficult to try to identify a given trap, whether it's donor type or acceptor type. And for that reason, we're not called upon to do that, fortunately. But let me just summarize for you that traps the closer to EC tends to be acceptor type. Okay? That is, they tends to be negative, which is not too surprising, although sometimes people find it surprising because they think of, hey, acceptor type should be like borons, which happens to have the acceptor states there. But that's you don't think that way. You really think about traps that are closer to the conduction band. Do you think they tend to be negative or positive? They're probably more like capturing electrons, right? More like some extension of the I'm not sure this is a good explanation, but at least to me, that's the way to understand that, is that they're more like electron states. They're closer to the conduction band. So it's not that surprising that traps closer to the EC, upper half of the band, tends to be acceptor type. Traps located in the lower half of the band gap are donor type. These are very common, almost universal. Different semiconductors behave also this way, although not many semiconductors have been studied like this. But in silicon, it's always like that. In fact, it doesn't matter whether this is oxide or even if it's a metal. Even Schottky, this concept also applies. All right, Schottky concept. That is the interface. The interface trap in the lower half of the bands are donor type. Upper half bands are acceptor type. Okay. All right. Next, we talk about density of traps. This time the density is not in terms just per centimeter square, but also per centimeter per EV. This unit is actually usually what's meant by this name density of interface traps. Although earlier I kind of said that, yeah, you could call this density of interface traps, but it's very rarely, this quantity is very rarely used in the literature. When you hear the term density of interface trap, it usually refers to this quantity, D, with this unit. Let me explain what it is, all right? The centimeter per centimeter square part is trivial. We're not talking about that. What's the per EV part? Per EV part is this. Go back to this arrangement diagram again. Think that there are many, many states. Imagine these are discrete interface traps, interface levels, all right, energy levels. Then we can definitely count the number of interface states per unit EV. Per EV is too large a unit, per milli EV, for example, right? And just so happens that density may not be uniform across the band gap, right? You probably expect there may be more of those near the band edge, fewer of those near the middle band, and that's absolutely true, all right? So typically what you find is there are more traps there and fewer traps in the middle. You do see in the literature often this curve drops down. In fact, I think I'm going to change this time. I'm going to take this away, because there are a lot of questions whether that data is real. In fact, I actually think it's probably not real. It's just measurement inaccuracies. We basically don't know what the density of the traps are right at the band edge. It's very difficult to determine that. But we do know that typically they show this trend that is a lower density near the middle and increasing as we move toward the EC and the EV. Yes?
Why would I suspect that there would be more traps near the
Because
band
one
edges?
way to think about the interface traps is a extension of the conduction band, extension of the valence band. Again, if we don't disturb this lattice at all, we don't expect any trap here. This oxide terminated the three-dimensional crystal, so we think there will be some traps introduced. It seems to be reasonable. Then still, if we first find the traps near the conduction band and valence band, all right? Okay, that concept is often used, for example, to understand the amorphous semiconductor. Or so we say, well, what it is now it's there's a lot of traps, a lot of energy states here now, and turns out energy states decreases exponentially from the crystalline band edges. So that seems to be reasonable. Okay. And from measurements, this definitely is what we see, all right? So I'll take this away. Kevin, please take that away. All right. So since we can have a different number of states per EV, now we can make a plot like this. And this curve that I drew there, we call that DIT. DIT has units per centimeter square and per EV, all right? Now, in general, can have all different shapes. I already mentioned it tends to increase toward the band edge. I also show you that we cannot rule out the possibility that perhaps in the middle there could be a peak. And this is interesting because this exactly is such a peak. Traps that's created by electrical stress or hot carrier stress, electrical stress, tends to create a trap at about 0.1 EV or so, 0.2 EV above the band gap, in the upper half of the band gap. By the way, just because we find this trap near the upper half of the band gap, what type do you expect to be? Donor type or acceptor type? You expect to be acceptor type. And therefore, if it's charged, do you expect it to be positive or negative? Negative or positive? Negative, right? Acceptor type can be negative or neutral. So it's true. Devices that have been electrically stressed tends to show you positive charge in the MOS system, all right? So, for PMOS, for NMOS, VT will change in different manners. One will become harder to turn on, another will become easier to turn on. And so that's why we need to understand these details about behavior of the traps. All right? Okay, good. All right, next. If we want to look at some equations, how would you relate DIT to things like QIT or NIT is probably a little better here. Probably NIT is a little better here. Yeah, I should have said NIT rather than QIT, I think. All right. Therefore, it's really. Oh, I put a Q here. I'm sorry. That's why I did this. All right. Let's put it this way. Okay. Let me do this. Q d NIT d phi s. All right. Let's see what we mean. I mean by that. Let me do it this way. Okay. And all right. Sorry, I will not do this. I go back to QIT. I think that is better. I realized I want to make a point about QIT. Okay, let's do it this way. All right. Let's go back to QIT. And in particular, I want you to look at omit the first equal sign. Look at the second equal sign. dQIT d phi s is equal to minus CIT. Let's look at that. What we're talking about that. All right. Now, if I now apply a VG. All right, some delta VG. We apply some delta VG. That's going to modulate this band gap. Is that right? Specifically, it will modulate the location of the Fermi level, or modulate phi s. Is that right? In other words, band will bend more or bend less. As phi s is modulated, can you see that QIT will change? Remember, because those traps under the Fermi level will be trapped, will be charged. Not charge is bad. Electrons will be present, and above the Fermi level, electron will not be present. Is that right? So as a result, as we change the d phi s, there will be dQIT. Is that right? Are you following so far? Anytime we see charge change when we change the phi s is always changed as a result of changing VG. We can say that we have introduced a new component of capacitance to the substrate capacitance. Do you agree? Yeah? So we call it CIT. IT is the right subscript. Would you agree? Right? So now you can say our equivalent circuit is even more complicated now. We have 4 components now. What 4 components? The first 3 I've seen before. The C accumulation, C depletion. What's the third one? C inversion. Now we can imagine there's a 4th component called what? What's that? Right, CIT. Exactly right. And CIT and dQIT ds is defined this way. Even the negative sign, you remember where that came from, right? Now let's look at the next, the first equal sign. Let's see what that's telling us. What is that telling us? If, as a result of a band bending, this is maybe not the best way to write down an equation to capture the physics I'm going to describe, but I think you will see what I mean. What I'm saying is that dQIT d phi s really is equal to QIT. Think about it. If phi s changed by 1 millivolt, right? 1 millivolt amount of these traps will move now behind from above to below the Fermi level. Right? Isn't that Q times DIT? That's how we define DIT. Is that right? Okay. This is very important because later we're going to have the task of how to determine DIT. We want to know what is DIT. We want to construct this curve. And the way we do is we're going to analyze the CV curve to try to isolate this 4th component. We try to cancel all these somehow and get this component. Once we get this component, we got DIT. See that? All right. So let's understand these 2 equalities separately. Because these 2 are equal, both equal to dQIT d phi s, therefore these 2 are equal. All right? Let me also warn you, when you really look through this, and I don't know how to reconcile this. Maybe I could if I spend more time, but I refuse to spend more time on it. Sometimes you'll find, maybe I should have 2q squared here because the units. The problem is that we call this per EV because we usually think of this in terms of energy band diagram. When you think of energy band diagram, we're supposed to be dealing with EV as unit. But you will find that sometimes you will see, in fact, I'll just tell you now. Turns out the interpretation of this will have to be V rather than EV. If you use EV, you will find we really needed Q square rather than Q, all right? But if you try to use Q square, you will find out the numerical value will be totally off by 10 to the 19th, totally unreasonable. So you should be able to catch that very quickly, all right? But it's unfortunate that if you even look at textbooks, the unit typically is given in terms of EV rather than V, and yet if you try to compare these dimensions, you will conclude it's V. And the numerical value people give to you, I'll tell you, is V, not EV. All right? Okay. Okay. For example, suppose we have an NIT of 10 to the 11th per cubic centimeter. What would be the average DIT? Would be what? 10 to the what per centimeter square and per EV? Let me tell you, it turns out 10 to the 11th. That simply is because we have one EV here, right? You divide that, so we say 10 to the 11th. It's okay? All right. So if you put the 10 to the 11th here, you multiply by the Q, everything looks just fine. All right? Okay. And so I'll let you work out. I know there's this lurking Q square somewhere, but just remember this example, you will see everything will work out just fine. All right? There's one Q here, not two Qs there. Okay. All right. So now we'll do what we said we would do is to try to determine this DIT as function of first phi s and then later DIT as function of VG. Okay? All right? All right? Okay. So there are several methods of doing that. I'll mention a couple of those. We don't need to spend a lot of time. This reminds me, I'd like you to give you some assigned reading. I'm making assignment out of these, the reader of volume 2. You know what I mean, volume 2, right? A lot of papers. By the way, feel free to browse through this. You don't even have to do this in order, sync with the lecture. But if I do remember, I will tell you to read certain things. If you read ahead of the lecture, no problem. Go do that, of course, right? So I will say read number 1 and number 4. Okay? Turns out number 2, 3 is a little bit out of order with my lecture. Every year I make some changes, and in fact, I cannot quite anticipate what I'm going to tell you in the lecture. So what I planned for the order for you to read is a little off from what I actually told you in the lecture. So I'll ask you to read the 2 and 3 a little later. But if you did read them, before I tell you to read, that's no problem either. Okay, so read number 1, number 4, all right? Okay. So this material you will not find in our textbooks. I think it's good for you to read some references there. All right. So one way to do it is you measure the high frequency CV. High frequency CV, I arbitrarily drew a rather strange looking curve. This is what you will see when there is significant density of interface traps. And as I said, anytime you have a new dielectric technology, you probably shouldn't be surprised to see CV curve like that. Or if you take a good MOS capacitor but apply electrical stress on it for a while, you shouldn't be surprised that the CV looks like that. All right, so now we're going to try to get some useful information out of the CV. Next, you compare that with the theoretical ideal CV. We all know how to draw ideal CV. We derived that equation in the last few lectures, right? Right? So we can do that as function of VG or as function of phi, either way, right? Phi s or VG. Is that right? Of course, this will require computers. You cannot draw this by hand calculation. It has a lot of exponential terms and things like that, right? Okay. Next, and this is what I want to spend time with you, is to think through this example, how to think about interface, how to think about interface traps. All right, let's think. We'll take any point on the vertical axis, take any C, draw a horizontal line, we'll get two intercepts, A and B. Intercept of the ideal CV curve and the actual CV curve. Is that right? Yes? They correspond to two different VGs. So same C, but two different VGs. Is that right? And what can we say about these 2 points, point A and point B? What is the same, what is not the same? Well, first, let's look at this equivalent circuit. Turns out equivalent circuit for these two cases are the same. Even though in one case, supposedly we have this extra term, CIT. In the other case, supposedly this extra term is not there. Is that right? By the way, I omitted several things. Let me tell you what I omitted. I omitted this, just to tell you, sorry. I omitted C accumulation. Why? Just because, let me tell you, we just cannot get anything in the accumulation region. The two curves essentially coincide, all right? It's not much we can get. Both have very, well, you know, they're both equal to COX, right? So you cannot get information. For the same reason, I really should have just omitted the C inversion for this reason, so that, well, maybe I'll leave there. Just give me an example to cross it out here, give you a chance to cross it out. We can omit this too, really. Right? So we really omit both. So you will say curve A should follow this equivalent circuit. I'm sorry, curve A should follow this equivalent circuit, only C depletion, and curve B should follow this equivalent circuit with C depletion and C interface trap, right? You might argue that. If you argue that, you get 99 points, really good. But you get extra points for realizing that we're talking about high frequency, and therefore maybe the traps cannot respond to it. And indeed, we're counting on the fact that traps cannot respond to it, all right, to this high frequency. The fact is that traps still traps in oxide, maybe separate from the interface by 2 angstrom, 3 angstrom. As a result, there can be pretty efficient tunneling, right? And therefore, the electrons can in oxide can communicate with the electrons in the conduction band or valence band. As a result, whether it's occupied by electron or not, will follow the same Fermi level as the substrate. That's the meaning of equilibrium, following that same Fermi level. But that's still not in this trap still not in the semiconductor. You cannot see that. I am sorry. Thank you very much for pointing out. I was pointing at this particular curve. I said it is true that when this interface traps crosses the Fermi level, it will change state from having electron to not having electron. But this may not happen immediately, depending on how easy it is for these traps to exchange electrons with valence band and with the conduction band. Does it make sense? Right? So perhaps it would not surprise you that this is actually, first of all, can be as long as hundreds of milliseconds. Okay, well, at least milliseconds is safe to say. Maybe as short as nanoseconds, depending on whether these traps are very close to EC or very close to EV, or whether they're very close to the middle of the gap. Right? All right? Okay. And so we're counting on the fact that these traps don't respond to the 10 megahertz or 1 megahertz of frequency. All right? Now, if they don't, then both two curves follow the same equivalent circuit, right? Because even the CIT would not show up under high frequency. It will show up under low frequency CV, but will not show up under high frequency CV. You see that? It not wiggle. Right? Okay. The same reason why the C inversion does not show up in the ideal IV curve, CV curve for under high frequency, right? There's no time for the electron in the interface traps to change with applied signal. So even CIT will not show up. They both have only this, and this is C depletion, I would say. Well, I'll get to that. Yes, question?
It seems, you said before that if you look at the traps as the distance from either EC or EV, that it follows a known distribution distribution. Is that true? Meaning that as we get to the middle, the density is lower than the outside.
Slower. Lower or slower?
Lower. So that you have more traps in your EC or EV and less in the center, right?
I don't know why you asked that. The reason is I has the answers. I gave you a counterexample. It's not necessarily as simple as that. If there's suppose a particular kind of bond, and I'm not quite sure what that is. In fact, I know in the literature, the chemists call this particular bond E sub B, and I cannot quite describe to you what that is. But certainly there's certain particular bond structure will give you a trap at a particular energy. So when that happens, there could be a peak. So it's not necessary. Yeah.
But then things in the center have a much slower response than things on the outside. So
Okay.
its effect in our life, that means that hot carrier really doesn't mean much because the response would be even lower frequency than the natural distribution of traps before that.
There are two ways to answer that. First of all, as far as I know, this is a very good research question, as some of you may want to do that. No one has measured the time constant of this particular trap. At least I don't know anyone has measured this. I have not seen this in the literature, all right? People have measured the response time of the trap in this, what I would like to call process-induced trap, whereas this I would call stress-induced trap. Stress-induced trap is something that has become more important as a result of device scaling, so hot electron effects. Whereas a lot of the information about this MOS system was studied in the 70s, and when people were not too concerned about stressing effect, they just want to understand the nitrogen anneal or fast pull or slow pull. So as a result, this particular peak has not been studied very much. I cannot answer you how fast that responds. But even if it responds slowly, it's still important because you could be biasing this transistor there for a long time, or even on average, it spends a lot of time where it should be charged, then still be charged. Right? It will not follow the immediate change in the Fermi level change, but over time period will follow the average, how much time it stays below the Fermi level or above Fermi level. That's the way to think about response time. All right? Okay? Okay. All right. Other questions? Okay, back to this. So given that we know, what we're talking about is that since we are having, we have the same, I'm going to change this to C depletion then, okay? So therefore, they have the same depletion. I'll change the C depletion, okay? Kevin, do make this change for me. If we already agreed that the both are following the same equivalent circuit, that means at A and B, C depletion is the same. If C depletion is the same, then we must have the same. Maybe I'll even add one point. Perhaps it will make you more comfortable. It's the same X depletion, and therefore the same band bending. All right? If you have the same depletion capacitance, that must mean these 2 points have the same depletion width, therefore have the same band bending. All right? Okay? So the question is, how can the two cases have same band bending, same surface potential at two different VG? Why should there be a delta VG? Why do we need a different VG to create the same band bending? Why don't you take a moment to think about it? I did say that the traps cannot be charged as a result of this high-frequency CV. The charge state cannot be changed by the high-frequency CV. But I did not say the traps charge states cannot be determined by the DC bias VG. Right? Right? Yes? So now do you see why we need two different VGs to create the same band bending? Because in one case, we don't have that extra component in this VG. In the other case, we have this extra component. Is that right? Do you see what I'm talking about? Yes? Yeah. Okay, I guess the circle also I did wrong. We should circle only this part, right? This is present in both A and B, right? This is present. I don't know what I was drawing that particular point. Doesn't matter. In that sense, I guess this circle is misleading. Of course, this is present in both A and B. This is only present in B. So if I do that, I'll make this change. Both A and B has that, right? This is only present in B. Is that right? You follow what I'm saying? Okay. It's for this reason. So now you can see how you get QIT. So for each C, you get a delta VG. But delta VG is our QIT, right? Based on this, we know delta VG is this. How do I do this? I'm sorry. Slow down. All right. So from delta VG, we can get QIT. So from this, we can get QIT as a function of VG. You see what we can get? For each QIT, for each VG, or for each C or each VG, for each phi S, all right? Okay, this is a little bit complicated. Let me slow this down, how to do this, all right? Just based on this, then we know at least for each phi S, let me call it H phi S, all right? So, you see, once we pick a particular C, we have picked a particular phi S. Remember, we know the phi S along each of these points. This is our theoretical point, right? Theoretical curve. We know the phi S corresponding to each point here. Is that right? So once we pick a C, we know the phi S. At this phi S, we know what the delta VG is, right? Because delta VG is nothing but QIT divided by Vox. Therefore, we know QIT as function phi S. Is that right? Yes? Therefore, we can differentiate QIT with respect to phi S because we constructed that. And that is equal to DIT from the previous slide. All right? From previous slide, remember, we had this relationship? Yes? So that's how, in principle, you will be able to create this, right? But you also still can only plot this as, oh, in this case, it's great. We don't even need the VG. I beg your pardon. I guess at some point I said that we wanted this. I take this away. We never want this. Actually, we always want this. Why? Because we only wanted to plot DIT as function of E, plotting from EV to EC. You know, near the valence band, how many traps we have, near the band gap, mid band gap, how many we have, near the EC, how many we have. I just drew an arbitrary shape here, right? And that position, each position is the phi S here. Think about the meaning of phi S. We're saying at that particular phi S, you know, when we bias at this particular phi S, now when I wiggle the phi S, what kind of dQIT, d phi S we get? And that differentiation will actually tell us DIT at that particular E, interpreted in this manner. Think about X, the horizontal axis, what that means, right? So when we change phi S, we mean we are scanning from EV to EC. So that's exactly what I want. Okay? I beg your pardon. I was wrong earlier when I said we want to change the DIT as function to VG. We don't need that. All we want to know is DIT versus E, and this quantity DIT as function of phi S will give us that exactly. Okay? Now to recap, we first get delta VG as function of phi S. That tells us QIT as phi X because the delta VG is related to QIT through Cox. Differentiating this once gives us DIT as function of Vs. And that exactly is DIT as function of E. We just reinterpret what is E. All right? E says is the energy. And when we change phi S, we're saying we're scanning the energy from across the band gap. That's what phi S does. As we change phi S, we're scanning the Fermi level across the band gap. Okay, I don't know how to use mathematics to clarify that, but I'm trying to clarify that with the subscript Fermi level, and if you wish, you can read this. But I think it's better just to explain in your own words to you the relationship between these last two quantities, what we're doing. When we scan phi S, we're really scanning the trap we're probing in the E space. All right? And the relationship is this. As we change the phi S, we're changing the E, we're scanning, we're probing. Right? Yes?
So all of this is done before the source and drain regions are diffused in. This is like a test so that you can get DIT versus E.
Not true. The question is, can this be done, if I can rephrase your question, can this measurement be measured on a transistor? Do we have to do this only in a capacitor? No? Yes, use a source drain region.
Right?
Yeah.
Well, because
Please.
when there's a source and drain region, there's a ready source of electrons. So
Oh, that's correct. Can we apply the high-frequency CV technique if we have a presence of the electrons? Yeah? Okay. The turns out the answer is yes, you can still do that. All right, that's maybe a little surprising for you. What happens in the high frequency CV, as you know, is this. First of all, I want you to realize that we're only using the depletion region portion of the CV curve. We're not using the accumulation region. We're not using the inversion region. Do you follow what I'm saying? We're only using the depletion region, right? Because in accumulation and in the inversion region, the two curves overlaps anyway. You really don't have any information. Yes? So as long as you limit yourself to the depletion region, whether you have source drain doesn't make a difference because that inversion layer is not formed yet. Do you follow what I'm saying? The inversion layer is not formed yet because we really are using the CV portion corresponding to the depletion. So whether the source drain region are present or not does not make a difference. Okay, that's number one. And number two, and I thought this is what you were going to ask, and I'd like to make this point. Suppose we have an inversion layer present. Does that change what I earlier said about there's a finite time constant of trap? When I said it's finite time constant, is that because there's an absence of electrons? I did not use those words. I used absence of electrons to explain why the inversion layer charge does not correspond to high-frequency signal. I did use that. I said because of lack of electrons. There's not a presence of electron. I explained the fact that the inversion traps, the interface charge does not respond to change in phi s by the fact that there is a physical separation between the traps and the semiconductor, not by the lack of electrons in the semiconductor. Even if there was a lot of traps charging the electron, even the inversion trap layer is present, there is still a significant time delay for electrons to move back and forth between the inversion layer and the interface trap. All right, so that's significant. Okay. So the interface traps would not respond to high-frequency signal even if the inversion layer is present. Okay? So either way, the answer is this measurement can be made in the presence of the source drain. Yes.
Are interface traps really quasi-continuous across the band gap?
It's at least assumed to be. You know, part of it is our ability to make these measurements are rather crude. So suppose there's some really fine structures, I suspect, has just been missed. And when you look at the data, it tends to be smooth. So yes, you can assume it's a continuous. And later we'll give you an interpretation also why. In fact, I'll give you the interpretation now, and I'll just use less time to talk about the interpretation is. Think about this physical space of the trap, all right? I think it's really helpful to think interface trap is really no difference from other traps in the bulk. It's just that they're closer to the surface. But how close is close enough? Well, it turns out they're very close. Well, they tend to have very short time constant, all right? And if they are farther away, there will be longer time constant. And in that sense, you can think it's kind of a continuous, all right? Thinking this SiO2 is amorphous structure. You know, where can this broken bond be present? It's probably semi-continuous. And indeed, this concept is actually used explicitly to derive some 1 over F noise. Later, we may have a chance to mention. I don't have a lecture plan, but I have a reference for you. This 1 over F characteristic come from the assumption that there's a continuous distribution of a trap in this spatial distribution. And furthermore, we assume the time constant is an exponential function of the separation between the trap and the silicon. When you make those two approximations, you end up with 1/f noise. Okay? If you haven't heard this term 1/f noise, I'll introduce that later, but some of the circuit design students probably have heard about that, and that's related to this. All right? So the assumption is it's all semi-continuous. Yes, continue. Please, continue.
I can see a spatial variation of these
Yes.
traps
Yes.
across the oxide, but are they also varying in energies?
Yes, it is. I already answered that. I understand. This is not related to what you're saying. Here, it is all considered continuous. Mhm. All right. Yes.
But that's for process traps, right? If you go back to hot carrier, it seems like you couldn't make the same assumptions regarding the distance of the trap from the surface.
It is true, yeah. Perhaps I answered that a little bit too hastily. I agree. I like that this description. It appears that so-called process traps, it's a continuous, but we already know one particular example. We know after stress there's one particular peak, and certainly one can visualize other types of chemical bonds that may give you discrete energy. So it could be, there could be discrete spectrum superimposed on a continuous background. Right. Yes. A fresh sample, you expect usually one smooth curve. Even when it's, and I like what he was, you just pointed out. You know, when you see this peak, in my mind, I kind of consider that as really a discrete energy level, but because our measurement inaccuracy gets broadened out. But it's also possible that it's truly broadened out just by the environment of this trap, being this is a amorphous material environment. So in that sense, it's also continuous. So you know, it's hard to say what it is. But anyway, we usually do see a continuous curve in that sense, all right? But this may be due to a particular specific discrete energy level, but that may still be broadened out by its environment. Still possible, right? In other words, there's not one very, very, let's say, clear bond that duplicates itself exactly from one trap site to another trap site, although they're pretty similar. As a result, they give us one peak. Okay? All right. Other questions, comments? All right. I do have other two techniques to mention. I'll use less time because I think the first example already gave you a good case study of what usually concepts involved to end with that, all right? But here I just show you some variations that you can do. One variation is to use high-frequency data and measure the low-frequency data. As I said, I don't like this name of low-frequency CV, so it's quasi-static CV, okay? So I'm crossing this out for you. And just to emphasize the fact that we're really comparing high-frequency quasi-static, all right? No one can measure low-frequency CV. All right. So you measure the high-frequency CV, and you measure the quasi-static CV. So you don't need in principle at least, you don't need any theory now. Now you can do something with it, all right? What you need is you need to pick one VG this time. Don't pick a C. Pick a particular VG. Let's say you pick this particular VG, all right? Pick this one, this particular VG, VG1, let's say, right? So we'll pick a particular VG1, right? Pick a particular VG. And that will give you a particular phi S. Because in this case, these two cases, A and B, share the same equivalent circuit, and both contain the CIT now, right? First of all, let's agree. Do they contain same CIT? My mistake. They don't have, sorry about that. Okay, slow down. Okay. All right, I should follow this carefully. Just say, same VG in this case give us same phi S. Why is that? Because both A and B case, both high-frequency quasi-static case, follow the same relationship. VG is equal to phi, or phi ms, let's say, phi ms, plus phi s plus or minus Q depletion divided by Cox minus Q interface trap divided by Cox. All right? And this is a function of phi s as well. When you look at that, if we have VG, we must have the same phi s for these two cases, because these two cases share the same equation. They both contain this term. They both contain that term. I'm pointing this last term. They both contain that term. Are you following what I'm saying? Because we're talking about DC bias, right? As far as DC bias is concerned, both of them contain all four terms. And therefore, the same VG at A and B, we must have the same phi s. If we have same phi s at these 2 points, then we must have the same C depletion at this 2 points, right? If we have the same C depletion, why do we have two different Cs? Why? Because they now have two different equivalent circuit. This is the equivalent circuit in the quasi-static case. We now have this extra capacitance. In the high-frequency case, CIT does not show up because interface charge does not correspond to the high-frequency signal. Yes? So therefore, this will tell us what? This will tell us the, well, I'll answer the question first. The question, please, ask the question.
Where's the inversion capacitance?
Inversion capacitance, in both cases, I have crossed out together with the accumulation capacitance. Again, there's no information we can get there. The difference is just Cox in the inversion layer. There's no information we can get here. They just coincide. So those totally go out. It's only applicable in the depletion region. All right? Okay. So now the question is, how are we going to get out of the, what does delta C tell us? Delta C is CIT. Not is CIT, but delta C yields CIT. Delta C reveals CIT. Right? Because we want to know this. And we know this, we know that. Do we know this? Of course, this we know. Do we know that? Well, at least we know the sum of these two, which is this one, right? The high frequency one. High frequency one gives us this, right? Low frequency one gives us three. So you only have one unknown. Can you solve it? You bet you can. I don't want to go through this, but the reading will show you how to even solve it. But you should be able to solve it, right? You have the two equivalent circuit. There's only one extra capacitance. You'll be able to solve it. Once you solve it, you know CIT. Next is physics now. What is CIT can be interpreted as? Can be interpreted as dQIT d phi s from our lecture number 2. Well, the concept from lecture number 2, this is from a few slides earlier. CIT is dQIT d phi s. Is that right? CIT is DIT. Remember that? I guess we don't need this term. I already emphasized 2 slides ago. CIT is DIT. If we can get CIT, we would have DIT. So here, you make use of that, you get DIT. All right? Okay. This is a little bit complicated. You have to find out from each VG what is the E, what is phi s. So again, reading will show you how to do that. It involves integration. All right? Still, you can do it without theory, but you need the integration. All right. Let's see, what else? Okay, I do want to end on this slide because, well, maybe even more, at least end on this one slide, okay? This is a technique that's kind of favored by people who has physics bent because, you know, look very physical. But in practice, there's a lot of problem with it. So as a result, I wouldn't say this is a better technique than the CV technique we just reviewed. But you do see this in the literature a lot, even more frequently than the CV technique because there has some appeal. I'll come to it, you will see, because it looks very interesting. What it is, I'll tell you what it does. What it does is the following. It applies a train of square wave signal to the gate. Particularly, let's use example, and this has to be done with a transistor. You have to have source and drain, all right? So we'll ground the source drain and ground the substrate, all right? Substrate, source drain are grounded. So bias condition is very simple. And we apply a square wave pulse to the gate, all right? And this voltage does go between, let's say, accumulation and depletion. Let's do it this way, all right? Or maybe I could say even between let's see, what did I do? I made it already accumulated and then depletion. All right, doesn't matter. We will see later. Maybe we'll go between inversion and depletion. It's not too important how we do it. We can change the V low and V high as we wish. Let's say V high is high enough for inversion and V low is somewhere in the depletion. All right? Is okay? All right. If we did that, let's see what happens to the traps. When we go into the high VG high, a lot of electrons come, all the traps gets below the Fermi level, so they get filled, right? Yeah? If there's an inversion layer, that's even better. That helps fill this traps, right? Even then, there's still a little time delay. So unfortunately, that's one of the limit of this technique. All right, we're not sure 100% of the traps is filled in the on state. We're going to assume that the on state is long enough so that the traps are all filled. Is okay? Right? Right? Okay. In fact, we can say all. Okay. Next, we suddenly change the bias to try to create this. So now the trap is going to be above the Fermi level. Is that right? Are you following me? All right. But will the electrons come out of the traps right away? Let's remember, there's time delay, right? So there may be some time before it comes out. Yes? On the other hand, the inversion layer should have already totally disappeared. Is that right? Very quickly disappeared after we move into this point. So at this point, electron come out. Where does it go? There's no inversion layer for the flow between source and drain. Is that right? Yes? So some of them will just flow into the substrate. Are you following what I'm saying? Yeah? And again, depending on the bias, maybe we can try to bias this very close to this, or maybe into the inversion layer, right? So that they go into the substrate. So the assumption is that all the traps that are released by all the electrons released by the traps are coming out into the substrate. Now, if we can count the electrons coming out of substrate, we will be able to know how many traps there are. Is that right? Now, we cannot count the number of electrons too small. But if we repeat this many, many times and measure the current, are you following what I'm saying? Then we can do that. Is that right? So what we do is put a very sensitive ammeter here. If there were no electron traps at all, there should be zero DC current, because this is a capacitor. But because of these traps, we'll get a DC current. And that DC current can be related to trap in this manner. It has to do with W, L, NIT, right? And here's in area, so multiplied by the area, we'll get a total trap. This delta indicate the kind of energy range that's being scanned by your bias. You choose the bias to scan a certain range of the gap, right? Times little electronic charge Q times frequency. Does it make sense? Think about it. The current will be proportional to frequency, right? Because every cycle you release this much charge. Yes? Okay? So this technique is called charge pump technique. But there's a lot of questions about this. You know, how about some electrons moving to the source and drain? And how do we know how much charge is released in the off state? How do you know all the traps are filled in the on state? You say, well, we long enough. We long enough, you don't get that much current because you want to count on the large F to get a sensitivity. Is that right? Use a short time, then you're not quite sure the traps all empty. So it's not necessarily a very quantitatively attractive technique, but you know, it's interesting, and you see this used probably more often in CV technique. Okay. All right. We'll stop here today, and see you on Tuesday.